example. This is the easier version of solids of revolution. This is the type that does not have any kind of a hole in it. So as you noticed in the video, and the example, a little explanation at the start, we were talking about volume by disks. And so a disk kind of means what it sounds like. It's literally a disk or a kind of a cylinder-like shape. And these, when we use disks, typically the shape we're dealing with is totally solid. There are no holes or concave parts to them. Like another way to think about it is there would be like no part that water could either pass through or be held by. No part of the solid, right? It's just totally convex everywhere. Does that make sense? No holes, no bowls, nothing like that. And so really, whether we use the disk method, which we're going to talk about today, or tomorrow we'll talk about the washer method, solely depends on the characteristics of the solid. And so today is super duper easy. We might break out the Play-Doh a little bit tomorrow. Today's easy to kind of visualize. We broke out the Play-Doh last year for a bit, just trying to visualize things and make a shape and try to understand what it looks like. So tomorrow and or next week early might be an appropriate time for that. So consider. But for now, we're going to be looking at just example number 2, and we'll spend some time reviewing. I've got a little review sheet for you. So region A is bounded by f of x, and f of x is a parabola. And it's also, region A is also bounded by the x-axis. We're supposed to find the volume of the solid formed by revolving region A about the x-axis. Lots of ways to visualize this. Here is one way. 2 minus x squared is a parabola. It's been shifted where? Up to. And it opens which direction? Downward, yep. You got it. So if you were going to graph this parabola, at least on the part we care about, maybe it would look something like, well, let's try that again. Maybe look something like that. Oh, no, I can't bring that in. Is that really true? Yep. You guys get it? Can you see it? Lenny, you're kind of giving me the sideways glance there.
Oh, no, I just have trouble seeing.
Oh, really?
Yeah.
Do you want to sit up closer?
No, it's fine.
Okay. All right. Well, anyways, so I'm sorry. This is just really bothering me. We're going to try this again. And we're going to put it in the right spot. So how about there and there and there's my parabola. Okay. So region A, I hope it makes sense that region A would be this, this green region that I'm trying to create right here. And what we're going to be doing with region A is we're going to be rotating it around the x-axis. And so I'll put a little notation there saying, hey, we're using this as our axis of revolution. So I always like to try to picture these in my brain. And I think, you know, you guys have maybe done this enough to where you could be like, okay, if I rotate this thing, what would result? Like, how would you describe the resulting solid?
Football.
I think a football makes a lot of sense. I mean, it kind of depends on how fat the parabola is, right? I might have misrepresented the fatness of it a little bit, but it's just a parabola. So it's like a kind of an oblong, football-ish kind of a shape. I think that's a pretty good description. So let's talk about a couple of principles. Make sure you either watched them on the video or maybe you remember them from previous efforts. Whenever you are rotating around an axis, like an x-axis or a y-axis or some line somewhere, there's always one principle that's consistent. The little representative element, the representative rectangle, representative disk, however you want to picture that, is always perpendicular to the axis of rotation. That's right. So because the axis of rotation is the x-axis, that means any representative elements, like a rectangle we draw in there, would have to be a dx wide, kind of tall and skinny type rectangle. It doesn't have to be that way. There's a different method, which would be a bonus topic, but I didn't put it in because we're getting so close to Thanksgiving and Christmas. There's a different method called the shell method, which often does not have to be used. There might be an occasion where that's the only way you could use it. And in that situation, the paradigm of the perpendicular to the axis of rotation gets flipped and it becomes parallel. Just so you guys know, if later on somebody refers to that shell method, that's what they're talking about. Instead of using like a volume of a disk, it uses circumference. It uses like rings or shells to build a solid. If anybody is real interested in that, it's not too hard to deal with. And instead of using a pi r squared concept, you use a 2 pi r radius or a circumference concept. So anyways, we could use, yeah, we could. It would be gangly for sure. It would be inconvenient on this particular question. Disks is definitely better, but just know that that's out there. Okay, so these representative rectangles are going to accumulate from left to right across the shape. We could draw them all in, but that would take forever, so I'm just going to draw that little arrow indicating that they're going to accumulate from left to right. So as far as our setup goes, we would say pi times the integral from where to where? Where would we start accumulating and where would we stop?
Isn't it like negative root 2?
Yeah, essentially these x-intercepts, right? And if you set the f of x equal to 0, that's exactly what you'd get, plus or minus root 2. So we'd integrate from negative root 2 to root 2. And what goes inside, of course, is r squared dx. So it's a pi r squared concept because we're finding the volume of a disk. So I'm just going to put blank parentheses squared, and it is dx because it's a vertical representative rectangle. Okay, so the radius is the distance from the axis of rotation out to the outer edge of the shape, right? From axis of rotation out to the outer edge, it's really the definition of a radius. So what would be a way, and I don't know how you're going to answer this, but what would be a way we could represent the radius? Well, yeah, so you could say f of x, right? Because the height of this representative rectangle correlates with the radius, right? And that radius is f of x, or that height is f of x. So we could do that. Of course, f of x equals something, right? And I think that's, if we're going to actually finish this, we want to put what f of x equals. So that would be 2 minus x squared. Want to be really careful because later on that radius is going to look a little bit different depending on the situation. But in this case, that's what it is. Okay, so this is a good setup here. If we were going to actually finish this out in this current form, what might be some of the things we'd have to do? Detail stuff. If we were going to move forward and evaluate this without a calculator.
Square.
Yeah, we have to like foil, right? We have to foil the radius in there. I agree. Okay, so we can do that. But I want to point out something else. Is there anything we could do to make, if we were going to do this by hand, is there anything we could do overall to the whole concept here to, in the end, probably make it quite a bit easier? Isn't there symmetry? There's symmetry to this, right? Because it's a parabola, so it's going to have y-axis symmetry. By no means do you have to do this, but you could take Caroline's suggestion and change your limits of integration from what we originally had to 0 to root 2. And in order to accommodate for that, we'd need to multiply the whole thing by 2, because of course if we do that, we're really cutting the volume in half, so we need to adjust for that by multiplying the whole volume by 2. Caroline, why would that be easier?
Because when you put 0 in there and you evaluate the integral, all the x's will just make it 0, so you don't have to subtract anything.
Right. Usually makes FTC a lot easier. That's exactly right. Makes sense? So by no means is that required, but it would be a helpful hint. All right, so take just a couple minutes here, see if you can take this thing all the way through to an end, and hopefully we can agree on an answer. And this will be our only one for today. Here we go. So if we are going to FOIL that, we get 2 pi integral from 0 to root 2, and then it would be 4 minus 4x squared plus x to the 4th dx. Make sense? And then we do our... Oh, thanks. I don't know why that does that. I need to adjust. So if we do our antiderivative, we get 4x minus 4/3 x cubed plus 1/5 x to the 5th, evaluated from 0 to root 2. And then really, to finish this out, we just need to evaluate it at root 2 and subtract the evaluation at 0. And of course, as pointed out before, since every single term in our answer has an x and there's no e to the x's or cosines or anything like that, we know that each term will go to 0, like you said. So to finish this one out, we could say that our answer is 2 pi times 4 root 2 minus 4 thirds root 2 cubed plus 1/5. I'm probably going off the other side, aren't I?
Yep.
Root 2 to the 5th. Sorry. There we go. I said it at least. And if you watch the video, it's on there. Yeah, so really in a free response scenario, this is as far as you need to go. I was over here talking to Sean. Sean did simplify this and he got 64 pi root 2 over 15 if you get a common denominator and add. And we confirmed that that actually is the right answer. So if you wanted to take it all the way through, I think Cameron might have done the same thing. And so yeah, so apparently that's how it works out. And it was 18 point something if you went to a decimal, 4.45 something, 956. Okay, good deal. All right, so that is a brief exercise with the disk method. Is that okay for you guys? Good remembering? Okay. So next time we will look at the washer method. There's a little video for that. So we're gonna get washers in, and we might do a little bit of volume by cross section as well. That was actually last year. That was the last thing we did, volume by cross section. That was the very, very last thing we did in March. So that might be one of the ones where you're like, oh yeah, that. So it'll be a chance for us to go back over that. So I figured you'd probably be okay with the disk method because we did that quite a bit. So anyway, awesome.